Alright guys, now that we've discussed how to find the distance and the slope between two different points in a graph, we can use this information to start proving properties of special quadrilaterals. So for number one, we have to prove that the opposite sides of a parallelogram are congruent using the following points. Now these points are already pre-graphed for us, but what this is asking us to prove is that the distance between AD and BC are congruent, and that the distance between AB and DC are congruent. So we're told that we have a parallelogram, which means that to start our proof in our statements and reasons chart, our first statement is that shape A, B, C, D is a parallelogram. And again, since this is listed directly in our problem, our reason for this is that it's given to us. But what are we trying to prove again? We're trying to prove that distances are equal to each other. So before we move on, we actually need to find the distances for every side. So to start, let's find the distance for AD. Now the distance for AD can be done either with the distance formula, and that distance formula can be written as D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Or you could do it with the Pythagorean theorem, where you could say side C, or your hypotenuse of the side, is equal to the square root of a squared, which is your vertical change, or your height of the triangle, plus b squared, which would be your horizontal change, or the base of your triangle. I typically tend to stick with the Pythagorean theorem because it's easier to write and visualize. So let's start with this side for AD. AD has a vertical height of 3, and it has a base length of 4. So to plug it back in, that means that side AD is equal to the square root of 3 squared plus 4 squared. And if I continue that through, I would have the square root of 3 squared, which is 9, plus 4 squared, which is 16. And if I add those together, it's the square root of 25. Now we can actually get a whole number out of this. The square root of 25 gives us exactly that. It gives us 5. One nice whole number to work with. Now, again, we're trying to prove that AD is equal to BC, so let's do the same with BC. BC is equal to the square root of its vertical height, which is 3 as well, and its horizontal length, or its base, of 4. Now, if you look here, for each side has a equal base length for their triangles, and each side of AD and BC has an equal height of 3 for their triangles. So write it out still, where our base is 4 squared plus our height of 3 squared. But since our numbers are equal to each other, we don't need to do the full math for this. We already know that these two will both end up equaling 5. So in this case, we could say that AD is definitely equal to BC. Now let's do it for AB is equal to CD. So for AB, we need to find our horizontal length and our vertical length. And for AB, we have a vertical length of exactly 1. And we have a horizontal of about 3. And again, another horizontal of 3. and a vertical of 1 for the other side. So looking here, again, since our triangles are congruent to each other on their heights and their bases, we can assume that AB is still equal to CD. So below, continue with the math for AB. We have 3 squared plus 1 squared. And if I multiply those out, I have 9 plus 1, which means that I need to take the square root of 10 to get my distance. Now again, since the triangles were congruent for their heights and their bases, that means that CD is also equal to the square root of 3 squared plus 1 squared, which gets us an answer of the square root of 10. Using the distance formula and the Pythagorean theorem, I've just proven that AD is equal to BC, and I've just proven that AB is equal to CD. So your next step here has to be that side AB is equal to side DC, which is equal to the square root of 10, and that side AD is equal to side BC, which is equal to the whole number 5. And the reason for that, again, is using the distance formula. Next, we have to take a look at what we've proven. Remember, we're trying to prove that opposite sides of a parallelogram are congruent. Well, using the distance formula, we've just proven that the opposite sides are congruent using that distance formula, which means our final statement is that AB is congruent to DC and that AD is congruent to BC. And since their measurements are both equal, we can claim that they're congruent by the definition of DEF of the word congruent. Again, if we are applying the definition of congruent using what we know about their measurements, we can use congruency to claim the final statement. And taking a look here, we've just proven in a formal way that every opposite side is congruent to each other. Next, we're going to look at example 2. And for example 2, we're proving that the diagonals of a rhombus are perpendicular using the following points that are pre-graphed for us. Now, diagonals exist in a shape through opposite points, which means that there's a diagonal connecting O to M and L to N. That's by the definition of diagonal. So let's start our proof. Again, we have to start our proof using a statements and reasons chart. So draw your statements and reasons chart, and we're going to be starting our proof in a very similar way to example 1. Just like in example 1, we're told that shape LMNO is a rhombus. So which means that your first statement will be that LMNO is a rhombus. And that's because it's given to us in the problem. So write given for your reason. Next, we have to claim our diagonals. And again, as we discussed, the definition of diagonals means that the opposite vertexes are connected by a segment. So for your second statement, write down that segment LN and segment MO are diagonals. And that's by the definition of the word diagonals. Again, we're applying that definition of what a diagonal is to claim that it exists in our shape. So if we know that these two are diagonals, we now have to prove that they're perpendicular. And to prove that something is perpendicular, we have to prove that the slopes of each line are opposite reciprocals. Now, opposite reciprocals mean that for one slope, we'll do slope 1, say it's a slope of 2. The opposite reciprocal of a slope of 2 would be an opposite sign, so it would go from positive to negative, and your fraction would flip. That's what reciprocal means. Your fraction flips on itself. So in your first slope, it's 2 over 1, which means here for slope 2, you would have negative 1 over 2. These two slopes would be perpendicular to each other in a graph. So let's find the slope of ln and OM. The slope formula is y2 minus y1 all over x2 minus x1, which means that for the slope of ln, we would have to do the y-coordinate for n. And our y-coordinate for n is negative 2. So we would do negative 2 to start. Again, if you cannot read this on the graph, you can read this above in the given points. So our coordinate is negative 2, and our x-coordinate for n is a positive 3, which means now we have to write down our coordinates for L. Now our y-coordinate for L is 0, so we're subtracting 0 from negative 2. But since our x-coordinate is a positive 1, we're going to be subtracting 1 from our 3. Solving algebraically, we have negative 2 minus 0, which leaves us with the original value of negative 2. But we have 3 minus 1, and 3 minus 1 gets us a positive 2. Now all fractions are considered division problems, which means that right now if I wanted to simplify, I would divide 2 into the top and the bottom, which means that I do negative 2 divided by 2 and positive 2 divided by 2. Negative 2 divided by a positive 2 gets us a whole negative 1, and positive 2 divided by positive 2 gets us positive 1, which means that your final slope for ln is negative 1. We're going to repeat the same process for the slope of OM. Now for the slope of OM, we would do m, OM, and we're going to say that our second coordinate is m. Like above, we see that 1 is our y2, and 4 is our x2. So if I'm subtracting away the coordinates for O says that its y2 is negative 3, and that its x is 0. Now pay attention here. Even though my y-coordinate for O is negative 3, I still wrote it in next to my negative. The negative doesn't take the place of your, or the subtraction side doesn't take the place of your negative. What it does instead is that you have to place it next to it, because what this is telling me is I'm subtracting negative 3 from 1. Now you can't take away something that doesn't exist, so that means your signs have to change to both be positive. So to solve algebraically, my numerator now is 1 plus 3. 1 plus 3 gets me a positive 4 up top, and since my bottom is 4 minus 0, that means I have a positive 4 on the bottom as well. So 4 divided by 4 gets me a positive whole 1. Now I could see that the slope for ln is negative 1, and that the slope for OM is positive 1. Both of these are the negative reciprocals of each other, or opposite reciprocals. So I can say with confidence that the diagonal ln is perpendicular to the diagonal for OM. For your third statement, we have to first write down the slope values of each and then declare that they're perpendicular. So for statement 3, write down that MLN is equal to -1, and write down that slope OM is equal to 1. This step is still important because we can't make a claim about the slopes until we know what they are. So your third reason should just be slope formula, which means your fourth and final one would be that based off of what we know of the slope, as stated in this proof right here, we can write that the slope of LN is perpendicular to the slope of OM, or more specifically, LN is perpendicular to OM. I would prefer you to write it like this because based on our slopes, we're able to make the declaration about the segments. So based off of this final statement can be claimed by the definition of perpendicular lines. That would be how you end this statement to prove that the diagonals in a rhombus are perpendicular. You have to use the slope formula here once to prove the rest of the diagonals are perpendicular. And finally, we're going to be looking at example 3. And for example 3, we're going to be proving that the diagonals of a rectangle are congruent using the following points that are graphed. So just like examples 1 and 2, we need to start our proof with what we know. And what we know so far is that shape ABCD is a rectangle. And again, since it is listed already in our problem, we can claim this because it's given to us. So before we can prove anything about measurements being congruent or they're being perpendicular or parallel, is that we have to prove that they exist in our shape. So we need to declare that there is a diagonal that exists from A to C and a diagonal that exists from B to D. Your second statement should be that AC, segment AC, and segment BD are diagonals. And again, we're using what we know about the definition and the key word of diagonals to declare that these exist. So your reason for AC and BD being diagonals is the definition of diagonals. So in this case, we're looking to prove that AC is congruent to BD. Now, since that is a little difficult to use the Pythagorean theorem with it, since both sides of the triangles are also at a slant, we're going to be using the distance formula to prove this. Again, we're going to be using the distance formula because we don't know the measurements of its height for each triangle, nor do we know the measurements for the base. It would be extra work if we use the Pythagorean theorem here. So we're going to be using the distance formula, which is the square root of x2 minus x1 squared plus y2 minus y1 squared. To start, we're going to be using AC. So the distance of AC is equal to the square root of their x2's, and x2 minus x1 squared plus y2 minus y1 squared. So let's use C as our x2. Our x value for C is -3, and our y value for C is -4. Next, we'll take the difference of our x and y coordinates for A. Our x value for A is 1, and our y value for A is 3. Next, we have to solve algebraically, which means that we have negative 3 minus 1, which is negative 4 squared, plus negative 4 minus 3 squared, which gets us negative 7 squared. Despite these being negative, we could still square them and get positive values. So we will get the square root of 16 plus 49. And if I were to solve that, that gets us a value of about 8.1 for its measurement. Now that we have the measurement for AC, we have to do the same processes for BD. Below, set up the statement again for BD is equal to the square root, and we're going to take D to be our second coordinate, just like we did with C in the first distance measurement. So, as listed, your x value for D is negative 5, and your y value for D is negative 1. Next, we'll take the difference of our x and y's for B, and our x value for B is 3, and our y value for B is 0, which means that we have the square root of negative 8 squared plus negative 1 squared. Now, solving algebraically, that means we have the square root of 64 plus 1, and if I were to solve that in the calculator, you will again get a measurement of about 8.1. Using the distance formula, we've just proven that AC is equal to BD. So for your third statement, write down that AC is equal to BD, which is equal to 8.1. And we're using the distance formula. Now, again, we're trying to prove here that AC is equal to BD, or congruent to each other. And since we've just proven that their measurements are equal, then by the definition of congruent, so definition of congruent, that must mean that AC is congruent to BD. And that's how you solve the properties of special quadratics.